Hello, everyone. My name is Gabriel Amazonas. I'm super excited to join you guys on the first edition of the Calgary Tech Talks. Really glad to talk a little bit about vector databases and how they work behind the scenes of AI. So let's jump right in. And yeah, before we move on, just sharing a little bit with you guys about my background and how we got here, right? So let's go. So yeah, as I said, my name is Gabriel Amazonas. I'm currently an engineering manager on the analytics domain at Nubank, which is the largest Brazilian digital bank in terms of number of customers. At the moment, we have more than 100 million customers worldwide. My background is as a formerly senior data engineer and also a senior software engineer. And Amazonas is actually my surname. I promise you guys, I don't work for Jeff Bezos, although I have a couple of years of background working with Amazon AWS solutions. I hold a couple of certifications related to AWS, and let's start to dig in into our topic. So, why are vector databases important? Let's start giving a couple of steps back in understanding about the data volume we generate on a daily basis. And according to Exploding Topics, which is a data analytics company based in Palo Alto, California, um, the global data generated annually is increasing geometrically each year, and we currently see a volume of data being generated on an annual basis of approximately 200 zettabytes, which is expected for 2025. And in the same report, Exploding Topics shows us that more than 50% of all global data traffic is video content, actually. And if we try to get a glance on the distribution of types of data generated worldwide on an annual basis, we can see that, as we mentioned, video is more than 50% of it, but a good part is social, gaming, web browsing, messaging. So, from that, we can infer that most of the data generated annually is actually unstructured data. So, data that is not stored in related databases where our columns and values are organized and have a specific type, right? So how do we actually handle all of these volume of unstructured data? And this is exactly where vector databases and what kind of data specifically they store come to the rescue, right? So in this image example, we exemplify how we can create vector embeddings and what exactly vector embeddings are. These are ways to represent unstructured data in a structured format. More specifically, we can represent data objects such as audio files, text files, and videos based on a machine learning model transformation and represent each of those objects as vectors of numbers. So here we are specifically using our fundamental algebra concept of vectors, and we can store that in a optimized way in vector databases, right? So from here, you can probably already have a grasp on what can we use vector databases for, given the fact that We can convert unstructured data into a structured format. What can we possibly do with that, and what are the use cases for that, right? So let's dive into an example use case to better understand which kind of use case we can work with this technology. In this text example, let's suppose we have a sentence database, right? And we have these three sentences in our example database. That is a happy dog, that is a very happy person, and today is a sunny day. And in the slide, we can see pretty much how would this data look like inside our database. In other words, after being indexed in our database, represented as vectors. Pretty much in our database, we would see something like a list of rows where each row have a sentence ID, for example, and an embedding value, which is basically a vector of floating point numbers that represent each text sentence, right? Okay, and let's say in this use case, we would like to compare new sentences with our sentence database and try to understand how similar or what are the most similar sentences to our query sample. As you can see from the image here, each sentence after the process of vector embedding and storing it in our vector database can be represented and matched against a new query example that will also going to be converted into a vector, and with that embedding value in hand we can compare how close to other sentences in the database this query sample is. And basically what this strategy is known for is semantic similarity search. In other words, this is how we can compare sentences or unstructured text data with other unstructured text data documents to understand how semantic similarly they are to each other. All right, so let's move on a little bit further to other use cases. Again, just to reinforce our example, we can now giving our vector database index of unstructured text documents. We can use common algorithm functions to compare vectors, basically. And we have a couple, like some strategies to compare vectors to each other. And further on this presentation, we are going to see one example of the usage of one of them, which is going to be the cousin similarity, but we actually have a few other ones that are also really common. Just to give a glance on how in how many lines of code can I implement this kind of vector embedding process using machine learning models and indexing that in a database, and finally searching for a given query in terms of how many lines of code would that be. Here's a code snippet that does all of the previous example that we just saw. And as you guys can see, these are pretty much something around 20 lines of Python code. So pretty straightforward, given the fact that the vector embedding creation model we are using is an open source one, which we are leveraging in importing here in our Python code. And basically, that's what it does. We iterate through our array of sentences, we create vector embeddings for each of them, and the final of these snippets, we query our database with our query example that we previously saw. Now, let's bring in a couple of examples of the databases offering themselves, right? So, what options do we have to use these types of vector database as services? And to dive a little bit more on that, I would like to share with you guys a couple of the offerings that AWS provides us. Let's just a moment. Let me check something here on my presentation deck. And all right. In a second, I'm going to get to those. All right. So back right at it. What kinds of vector databases offers do we have? And to talk a little bit about it, I brought to you guys from AWS documentation in the vector databases topic, which kinds of vector database they offer. And here, as you guys can see, we have Amazon Open Search Service, which is a example of vector database that fits exactly the sentence database example that we previously saw. We also have Amazon Aurora PostgreSQL with the PG Vector plugin that also enables on PostgreSQL installations to index vectors and to run this kind of workloads that we mentioned in the previous example, but also this is exactly the offer that we are going to view in a little more detail in the final of this presentation in the coding demonstration. You also have Amazon Neptune ML, which is a graph database offering on AWS. Um, and we have Amazon DocumentDB and Amazon MemoryDB as well. All of those having under the hood or more explicitly providing the features that enable us to work with vectors inside the databases, and especially how to index them so they can be queryable, searchable based on the vector content inside our storage database layer. All right. So now, time for our code demonstration. Let me check here, guys, if I can share my screen. And here we have another implementation example. This time I'm going to walk you guys through all of the steps for a example use case of searching for images with similar context. And for that demonstration, we are going to use PostgreSQL with the vector extension enabled. Okay, let me share my code screen. Just a moment. Here it is. Let's go through each code block step by step. Here we basically start by installing a couple of binaries related to Postgres, NumPy, PyTorch, and pgvector, the plugin itself, right? So as you can see, a couple of pip install commands, and after that, we basically run the PostgreSQL service in our environment. We then proceed in the second code block here to create a specific user named admin with its passwords and a super user profile. And we create a specific database for our demonstration here, which we named ImageDB. We grant the privileges on the database to our user, and we alter these users to be using our queries along the code further here in this Google Colab notebook. Just to be more explicit about it, of course, this isn't something that we recommend to configure a production vector database environment. Okay, this is just for the sake of demonstration purposes and to enable a vector database specifically in a Google Colab notebook. In production, we would recommend something like containerized environments and self-contained environment variables in a properly secured way. Okay, so let's move on with the PostgreSQL instance usage here in the Google Colab. As you can see, there is a very specific SQL operation that we need to run in Postgres so we can enable the vector extension. And this command is create extension if not as is vector, right? Moving on, here we have a couple of SQL commands that we use to validate that everything is set up on the database and including the vector plugin configuration. And here we proceed to start our operations with our vector database, where the first is we are here at the SQL statement creating a table named image embeddings with three columns, one being a ID, which is a serial primary key, auto-generated and handled by the database, a image name text column, and most importantly, a column named embedding, which as you can see has its type defined as vector 1000, having 1000 as a parameter for this vector type, which states that we are expecting to store vectors, or in other words, arrays of floating point numbers with 8,000 elements specifically. So keep that in mind as we proceed to understand the next code blocks. Okay, let's move on. Right next, we have the code that actually converts our vectors to vector embeddings. Just like the sentence database example that we saw, here we are going to work with images of cats and dogs. And to convert these images to vector embeddings, we are leveraging a already pre-trained machine learning model that works with images and knows how to convert them to embeddings. In this specific case, we are using the ResNet 50 pre-trained model to transform our database of images or our image folders to vector embeddings, and we proceed to iterate over our image directories, convert all of them using these pre-trained model ResNet 50 that we mentioned to vector embeddings, and we execute finally a SQL command to insert them in our vector database. We basically run insert into our table image embeddings, passing along the parameters image name, which is basically the name that we retrieve for these from these image directors right here, cat1, cat2, cat3, as you can see. Just a second. And we pass it along to our insert into command with the image name values and the embedding itself values that now are going to store our arrays of 1000 floating point numbers, right? This is a very important part of our code here where we are running exactly the process that we previously mentioned. First, converting our unstructured data to vector embeddings and then indexing them in the database so they can be queryable for similarity context, right? So in the next code block, we are going to retrieve one of the images that is present in our image directories from the database just to validate that they were actually inserted there in the database, and they have the correct structure that we would expect, being having a image name column and an image content embedding. Here, as you can see, we are basically opening an image based on the image name attribute that we just retrieved from our database. And just for the sake to be more specific on what kind of search we would like to do, as you can see, we have very different from each other cats, right? We have a couple of black cat images in the database, and we also have these little white cat here stored in the database. As we would expect, if we search our database based on an image of a black cat, we would definitely not expect to retrieve this white cat right here, okay? Their vector representations should be quite different from each other. And on the next code block, what we do, let me clear the output that I previously ran before this conversation. What we are doing now is let's select from our database table the most similar image to the image that we are querying our database against. So the whole process would look like I want to search my database for an image similar to the image I have in my hand, okay? What should I do first? First, I need to convert my query sample to a vector embedding. Now, I can query my vector database searching for images that are similar to this vector. And as you can see, we have this select clause with a very specific order by embedding, which is a vector type column, using an operator that is specifically available if we have the pgvector plugin enabled. When you do so, now we can compare the vectors. These very specific operator implements the causing distance vector comparison methods or algorithm that we saw earlier in this presentation, right? There are other operators that implement other vector comparison methods, and all of them are available, and you guys can check them out on the pgvector extension plugin documentation, okay? But in this case, this implementation compares these vectors using the cousin distance for similarity context search. Now, we are searching our database with this specific black cat picture, and since we have just three cats stored in our database, and two of them are black cats, one is a very different white cat, we will definitely expect that searching with this image, we locate the other black cat in our database, right? And that is exactly what happens when we query our database comparing the vectors that represents those images. Pretty cool, right? That's really, really exciting. It works just fine. And moving on, I'm going to be more specific here with you guys and show what are the other images in our database, like the docs folder have three images that were also stored in the same vector database. And just to show you guys that they are not expected, of course, to be returned as a result for this search using the black cat as a query sample, because their images look very different, of course, from our query sample image, right? So we just saw a live code example of context similarity search based on an image that is converted to a vector embedding and is used to be compared with other images stored as vector embeddings in the database. Now, at this very last code block, I'm just querying all the databases for all the image name attributes available. So you can see there are actually six images in the database, and our query and comparison ran against all of the six images, right? Very cool, super exciting. And finally, here I'm just demonstrating how the embedding column on each row would look like. As we mentioned, they are vectors of 1000 floating point numbers. So it's a little bit difficult to see them here in this kind of image display from Google Colab, but you can pretty much see that there are a lot of floating points numbers in this array. And yeah, I think that's it for the demonstration itself. Guys, I really would like to thank you all for being here, being present at the first edition of Power Tech Talks. This is a super exciting moment for me, and I hope you enjoyed the content. Please feel free to reach out to me on my LinkedIn. Here's the QR code.